Nitinol, which stands for Nickel Titanium Naval Ordnance Laboratory, is a superelastic shape memory alloy composed of near equal parts of nickel and titanium. Superelasticity means it can be manipulated to change shape when a force is applied, and as soon as that force is removed, it will bounce back without deformation. Shape memory is a similar property. However, the difference is that when the material is deformed, it will stay that way until heat is applied, at which point it remembers its trained shape and goes back to its original form. Above a certain critical temperature, called the transformation temperature, the material will be superelastic. Below it will have shape memory. The transformation temperature can be controlled by slight changes to the ratio of nickel to titanium and by secondary manufacturing processes. Nitinol makes a great biomaterial because of its excellent biomechanical properties, damping characteristics, and corrosion, fatigue, and kink resistance. However, it is a really tricky material to work with because the superelasticity makes it really difficult to machine. Though it's not impossible and this material is machined every day, it means that designs in nitinol are limited to what can be formed from wire or cut from a rod or plate.
This is where 3D printing, specifically SLM, comes in. It would allow the designer to break down those walls and build shapes that haven't been possible before, and go as far as creating custom geometry for unique patient anatomy. SLM involves a metal powder that is deposited in thin layers, which are melted by a laser. Successive layers are built up to form the desired part. This technique could be particularly useful in treating complex balloon aneurysms that are difficult to address with current methods such as coiling.
So how do you 3D print nitinol? This method uses a mix of elemental nickel and titanium powders. Pros: the designer can control the ratio of nickel to titanium and therefore the transformation temperature. Also, it's much less expensive compared to pre-alloyed nitinol powder. Cons: this method is more prone to variation, meaning defects that require extensive process development work, and it may not be easily adaptable for the small scale required of stent building.
So after mixing the powders and setting the parameters, the printed sample needs to be characterized. It's important to verify that it is substantially similar to traditionally manufactured material. The sample is first removed from the build plate using a wire EDM, which stands for electrical discharge machining. This machine uses an electrical current to cut through the metal samples. After mounting and polishing, the sample is analyzed under an optical microscope. The material must have a high density level and show no evidence of microcracking to be viable. Microcracks, if found, are a fatal flaw in the material's design and are nearly impossible to eliminate. In this sample, there are no microcracks, but there are a few macrocracks from the high energy of the laser. These can be fixed through future process modifications. The next step is then to analyze the material composition under a scanning electron microscope with energy dispersive X-ray spectroscopy. This machine can identify the elemental composition of the different areas of interest, such as defects, and give an idea of some of the phases present. This sample shows regions of unalloyed particles embedded in the material, mostly concentrated around the edges, and some quick calculations show that the surrounding material is mostly NiTi, which was the goal.
This project is still in its early steps with work to be done, such as solving the macrocracking issue and developing the material to perform at scale. However, there is a huge potential market for its use. Our goal is to see this material open doors to clinical applications of nitinol that are currently unexplored.